Okay, we're on the second day of spectroscopy, which was the interaction between what and what, everybody? Light and matter. That was the first question on the quiz. Okay, we have just some general terminology of light and its interaction between light and matter. First one is diffraction. And to observe diffraction, the light, which could be visible, it kind of helps, otherwise you're not going to see the diffraction, right? But it doesn't have to be visible light. Has to be coherent if you want to observe diffraction. Coherent radiation is necessary to observe diffraction patterns. What does it mean, Kathleen, for radiation to be coherent? And there's some hints up here in the little pictures. Looks like what?
We use those words.
Yeah, they're all in sync, right? All the crests are lined up and all the troughs are all lined up. So you could have a incoherent process going on, like a flashlight or something, right? Or you could have a coherent light source. Okay. What is diffraction? Pablo, what is diffraction? Now, if we didn't have hallways, for the sound to bounce off of, there's no way you could hear my voice right now without diffraction. Impossible. That's a hint. What's diffraction? Kind of. It bends around edges and things, right? It's almost like you have to imagine being in a swimming pool, right? And here's a corner, and there's no borders on this swimming pool, right? So kind of a huge swimming pool, right? And I'm sitting here making some waves, right? The waves just don't go in this direction along this border, and right? Pablo starts feeling some waves, right? Waves bend around corners. You can't stop it, right? So does it sound like diffraction is a particle or a wave property? Definitely a wave. If it was a particle, man, it'd just keep going straight, right? That little, it never hit Pablo around the corner. A circular diffraction pattern. What does it look like? Well, I'll show you. I'm going to, first I need coherent radiation. So easy, cheap source. Coherent radiation, a laser pointer. And you're going to have to get out of your seat to see this, because once you observe it, you need to sketch it, right, in your notes. So I got to find my I'll just make a new hole. That's easier than finding an old one. Okay, so I need to make a circle. So all I did is made a circle with something sharp through aluminum foil, line up that guy with that. All right, now you got to, let me stand farther back. It might be better. And then you have to go up and see it. So you're going to have to get out of your chairs. Well, let me shine it up there, and then you can see where you're going. All right, now you got to get up there and see it. See what it looks like so you can sketch it. What does it look like? Oh, sorry.
Starburst looks like nothing.
What do you see in the center? Now you should see dark, bright, dark, bright, dark, bright, dark, bright, dark, bright, right? In circles. If you don't see it, you better take a closer look. You have a bright center, and then you have dark, and then another circle, then a dark, and another circle, dark, and another circle. Right? Yeah, oh yeah, that's a perfect example. Perfect idea of it, description. It looks like a target. That's exactly right. So everyone saw it? So make sure you make a sketch of it. It'd be a good quiz question. All right? What does a circular diffraction pattern look like? You can't observe that just shining a flashlight through a hole. right? It won't work because the light's incoherent. It has to be coherent. Okay. Addition of waves is complex, right? And because just imagine we're talking about spectroscopy, and from your we're used to thinking of maybe what you hear, they're waves, but it's not this sort of wave. Sound is what sort of wave?
Longitudinal.
It's longitudinal, right? Light is transverse. Sound is longitudinal. Its oscillation is in the same direction as it's moving, right? What is sound? It's in air, but it's longitudinal. So my little vocal cords are either pushing it. It's like a speaker. Imagine a speaker is a lot easier to think of because a speaker can just go out or in, right? So either it's compressing the air or it's pulling back, so making a high pressure region pushing out or a low pressure region. So compression and rarefaction is really what sound is. But anyway, you could have my voice is a whole bunch of different waves that you're hearing, right, all at the same time. But they're all just kind of, a big blob is what you're hearing. But if I just take two frequencies, and you'd think that would be pretty straightforward, right? Here's one frequency. Let's see if I can get a. Can you hear it? Here's another frequency. But doesn't it sound pretty much the same? One is 320. Oh, I didn't hear it. Let's see if I can hit it on something hard. Yeah, how if I hit it with a nail? There's that one. There's that one. Okay. Yeah, I might just hit it sharper. But they both say 320 on them. So they're both supposed to be exactly the same, but one is actually 321, the other one's about 322 or so. They differ by about 1 hertz, and I know that because if I add the two, if I bang them both together at the same time, right, one is emitting 320, the other one's emitting 321. A little vibrato. Now, they're going to call it beats is what we're going to call it, but now, the only way for you to hear it is I got to put it way up here. Then you hear this wah, 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 wah. Right? And that's just two frequencies.
Yeah, that's pretty annoying. How do you spell wah, wah, wah? Just put W.
You hear it? Let me know if you hear it. Otherwise, I'm going to stand next to you the whole hour. Do you hear the wah wah? So what I'm trying to get across is if you have something like a FTIR or UV vis, look at all the, it's almost a continuous spectrum of wavelengths, frequencies, same thing, right? This is just two, and you're hearing already something complicated, a wah, wah, wah. So that's what I'm trying to get across here, is that this is really complex stuff, that these, crests, constructive, destructive interference, the whole gambit. Okay. And did you notice that what you heard, and that's just two frequencies, that beat, that vibrato, was at a frequency that was the difference between the two sources. That's how I know they're off by about, because you hear about wah, 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 isn't it about 1 per second? So that means the frequency difference has to be about 1 hertz. Yeah. Okay, exactly. Refraction, reflection, or diffraction? Refraction, reflection, or diffraction? All right, let's pick on somebody here. There's several examples here. Alice, there's A. Which one is that? Refraction, exactly. All right. Robert.
I knew you were going to do that. I can't see if that's the picture. Do you have those two fields now?
What is going on in B? What's that?
Diffraction with the prism.
It's a glass prism. White light's going in. Roy G. Bibb's coming out.
Reflection. Does reflection only just be white light?
Good point. If it was reflection, it would be white light again.
Yeah. Well, I had a good point, actually. I've eliminated reflection. Adam will take over.
Yeah. We're used to, right away we jumped to the glass, and we knew that was refraction. Nobody questioned it. We're very comfortable with that. But you change the medium from water and air to simply glass and air, all of a sudden we lose the refraction idea. Isn't that curious? It's some misconception type of thing going on up in the head. But that's just refraction again. How about C? Anna, how about C? You only have these 3 choices here. Somebody help her out? Friend is phoning her. That ain't gonna work.
Isn't it
Diffraction. Yeah.
And what is
All right.
that?
So this is. Do you see the waves that are hitting this little slit, and then they're sending out this weird kind of. Yeah, they're bending around the corners, kind of, right? But they're adding up, constructive, destructive interference. And notice how the incoming light has to be coherent. Okay. So you have this incoming light, and then it's bending around the corners a little bit. How about D, Emily? It would be diffraction again. Yeah. How about E, Sandy? Yeah, refraction, right? You try to shoot a fish, and you're going to miss them if you go straight. Oh. F, Ricky?
I'm just going to go with diffraction. With E, I'm sorry, we're talking about E.
No. E was refraction. F. We're talking about F now.
Yeah, my guess was diffraction. I mean, I'm not.
Is there any difference between F and B?
I don't know, it looks like the light's straight in F.
In F, the light is straight. What's the difference? They're just using a what? Starts the G. A grating? Right? They're just using a grating to break up Roy G. Biv. In B, they're using a glass prism. Okay? So this is just a much more efficient way. F is. Right? So it's still... Yeah. Hold. Let me think. No, I don't think so. I think now grating operates on a different principle, doesn't it? A grating has... How does this thing work? How does this thing work?
It's like it diffracts.
How does this thing work? It has, in order for you to see red, for example, its little lines, it has to have, maybe, don't get rid of the word lines. It needs to have periodicity that's exactly the same as the wavelength of red. For example, an oyster shell. You see the colors on an oyster shell, right? Does that have nice, perfect lines that match red? No. There's periodicity in there for the little calcium layers. All they are just layers. And they're just laid down in an order that's very, very periodic. That matches the wavelength of red, so it reflects red. If it matches the blue, then it will reflect blue. Okay, that's kind of how that opal stuff works. So diffraction grating, I know it's lines, but it doesn't have to be lines. It just needs to be periodicity. Yeah, it's diffraction. It's diffraction.
All right. So I have a question. Is it bending those things, or are they just showing that detail to show you that the light gets spread?
They're diffracting. It's diffracting. Bending might be a better word for refraction, because different colors travel different
Because it looks like the angle's different when the white light hits it and went like red, for example.
Well, white light goes straight through. It's not diffracted. White light travels straight through. It's not diffracted. How about G?
Is it more of these or is it meters?
Okay. Now G is, it's just one of the, when you look at a grating and you see the colors, so G would be diffraction again. Yeah. And finally H, reflection. Yeah, H is easy. Okay. The Fourier transform. Now we have Fourier transform, John, in one of our machines. Which machine is it? Upstairs in 415. Which machine is it? Yeah, the IR. But we don't call it the IR. The FTIR. FT stands for Fourier transform. Okay, infrared spectrophotometer. So, what can a Fourier transform do? If you take a signal, signals can be really complicated and ugly. Like you take a microphone, right, and just see put it on an oscilloscope, and you see all the signal versus time are just bouncing up and down. If I was just talking, it would just keep going like this, right? But if you, start the recording, stop the recording, and get all that information. I mean, there's a lot of information. Just think of all the frequencies. They're all at different amplitudes. All these different waves are adding up in a very complicated way. Well, you apply a Fourier transform to that. All right? Apply a Fourier transform, and then you get all the individual frequencies out of there and their intensity. So it's really powerful. You get out all the individual frequencies and their intensity. So essentially you get a spectrum, right? You get a spectrum. You could plot frequency versus signal, right? The amount, and you can get a spectrum. Now they like hanging it down here for FTIR. Whoop, this individual frequencies, right? You get a Fourier transform. You get an infrared spectrum. Now I lost my good animation, so all I have is this one now, and it's not near as good. But where's play? Huh. Oh, no wonder it's coming out of here. All right. So, the spectral region isn't that great because, all right, it's only showing so many frequencies, and those are probably frequency ranges, highs and lows. All right. I was looking for a better one that actually showed, individual frequencies. So you have this whole lot of stuff going on that it would look more like. That would look more like this.
There you go.
But I can't find it. Now, in PChem, we have a spectrum analyzer, and we're going to use it to illustrate the Heisenberg uncertainty principle. We just haven't got to those labs. If we ever finish Spartan, we'll get to it. Okay.
Does anybody even remember?
So we have, let's get in. So matter can diffract, reflect, or refract, right? But it could also scatter, okay? And there's two types of scattering. The first type is Rayleigh. It occurs when the scatter is smaller than the wavelength of light being scattered. There's no change in frequency. So if Rob is a Rayleigh scatterer and red light strikes him, what color is gonna bounce off? Red, right? No, there's no change in frequency. It's like what type of collision? Elastic or inelastic? It's like a elastic collision. No energy's lost. Okay. There's no change in frequency. There's no change in color. The shorter the wavelength, the easier it is for a Rayleigh type scatter to scatter radiation. Okay. So we have fog. You want to shine light through the fog. You want to sell these fog lights. What color is best, or does it even matter? Adriana, does it even matter? Now, I'll give you a hint. This whole fog thing is Rayleigh scattering. These water droplets are tiny, 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 tiny.
Oh, so then it would be blue.
Now, the color that you're using on your fog lights, do you want it to penetrate the fog? Or do you want, you want to penetrate, you don't want it to be backscattered on you. So you'd pick the longest wavelength, right? Would be red. The problem with red is what? Now, red would penetrate definitely the deepest and the farthest. How sensitive is your eye to red? Right? What are the colors that you can see? What are the colors that you can see? What's the name of the guy? Roy G. Biv. Okay, there's a reason why red is on one end, violet's on the other. Your eyes are falling off at those wavelengths. Are your eyes equally sensitive to all colors? Definitely not. What color seems bright? Yeah, yellow definitely. Yellow's bright. Okay, so red may not be the best because your eyes aren't that sensitive to it. So that's why they pick what color for fog lights? Yellow, or sometimes you see orange, but usually it's yellow, right? Yellowish. This is kind of...
So what happens when they have the white lights?
White light has... All right? White lights aren't going... White lights have what color in them that's going to backscatter a lot? The answer is really down here, this one. You're driving down the road, and some dudes have these really freaking bright lights. They just...
Yeah, the blue LED one.
They're bluish. They have a bluish tint to them, right? Now, if you're in that car, the road probably 5 feet in front of you is just super bright, and you can see great. But try looking a quarter mile down. Try the guy approaching you. Those lights are so damn bright. It's horrible. It's just a big wall of light in front of those people. They should be illegal. Why does it do that? Why is it so bright? Why? What is it about blue? It's really, really what? Short. So it's going to be really, really easy to what? Scatter. There's no fog even. It doesn't matter. Those lights, there's air. Right? There's dirt, there's dust, but it's just air, man. Those blue lights are horrible. Okay? So what's wrong with white light? Well, yeah, there's some blue in there, right? So it's going to backscatter on you. You're not going to be able to see the red portion or the orange that penetrated the fog. This is still going on. LED lights on electronics are really small. We have a alarm clock at home that has this color LED lights. You can put the dang thing on as dim as possible. Still lights up the whole room.
The little blue light things that they put in computers. Because those are like freaking lasers.
Blue isn't so bad. For me,
Okay.
it's that lime green color, right? That lime green color just lights up the whole room. You notice that? And they still use those things. I don't know why. It's crazy. But is it because that LED is so powerful? It's because what? What is right in the very center of Roy G. Biv? Green. I'm not sure how the sensitivity of your eyeball works, but my guess is that it might be somewhat of a bell curve, or approximate. Green's right in the middle.
Are you serious, dude? Oh my freaking God.
What's that?
He didn't know what Roy G. Biv was.
Red, orange, yellow, red,
God.
red.
Gotta ask. We gotta ask some questions there, dude.
Even Ricky knew that.
We have a new Alamo.
Okay.
Okay. So we're still into scattering.
What did he say?
Why is the sky blue during the day, and what color is the sky during a sunset, and why? Let's start with the blue one, Kathleen. It's not the blue oceans. It's the nitrogen in the air. What's so special about nitrogen? It scatters. It's an excellent blue scatterer. Exactly. It's a Rayleigh scattering, but that nitrogen molecule, now, because we're really glossing over all the mathematics of this stuff. We're just making general statements. So if you look in the mathematics, you see that the size of that nitrogen molecule makes it an excellent blue scatter. So you go to any planet, anywhere in the universe that has mostly nitrogen in its atmosphere, it's going to be what color? Sky. Blue. Methane is an excellent red scatterer. You go to any planet, right? Mars, there's a lot of methane, has a reddish hue to its sky. Okay. What color is the sky during a sunset? A lot of methane? What? What's going on there? What color is the sky during a sunset? Well, obviously it kind of shows. It's reddish. But why?
Isn't it like the air's changing, you're changing temperature and
Is what? Dust?
Kansas song.
Okay. No one has an answer? I'm gonna have to draw a picture then. Anyone has an answer?
I have a question.
Yes.
But this is like, so then the sky isn't blue because of the reflection of the ocean? What?
Not at all.
They extend that into
The sky is not blue because of the color of the ocean. For sure.
Isn't the ocean blue?
That makes me mad when like really official sources say stuff like that,
Yeah,
and you
in
find
the
out it's
commercial-
wrong,
in the
and you're like,
commercial
what
it
the
says
hell?
that.
Take Jim Kimmel Smith and then Analytical will tell you that he lied before.
Okay.
I'm so mad.
So here's the sun,
I was like,
right? Now here's Earth. I draw a little dude on him, right? I'll draw a little dude on the Earth. Where is he standing if he wants to see a blue sky? In other words, it's the middle of the day. He looks up. Where is he standing? Now, if he's on the back of it, it's nighttime, obviously, right? So he's got to be standing up here somewhere, right? He's standing, I don't know, right around here somewhere. How do you draw a dude? All right? He's standing around there. Okay, now it's going to be this time, though. Now he looks up. I got to draw this bigger now. Now he looks up and he sees a red sky. Okay?
Something about long wavelengths, right?
It has a lot to do with long wavelengths.
Oh, is it diffraction or?
Now, the dude is, you're right, it's sunset, so he's just on the border going to behind the planet, right? So if I could draw this three-dimensionally, which I really am not very good at, all right? But I don't know, put the dude right in here somewhere, right? And the Earth rotating. Okay. Which one, during the day or sunset, is there a lot more atmosphere between the dude and the sun? In the day, he looks straight up, he's got this much atmosphere. I don't know, if you sketch in the atmosphere. During the sunset, he's got a lot more atmosphere to get through. That light does, right? A lot more atmosphere to get through. Much more scatters. That's all. So what's the color that is the most difficult to scatter? Red. So you see a reddish sky. If you're an astronaut, Pablo, and I'm going to blast you off, just go straight up, right? How would the sky change colors? Let's blast you off in the middle of the day, so it's blue right now. Would the sky change colors on you? So with the sunset, it'd probably be best to blast him off during sunset. He's going to see a lot more change in color. But let's just stick to the day since I started with the day. You start with the day, and you'd have to Google for some pictures, and it works. These guys are blasting off. The farther they get out into space, they're still in the atmosphere. What's the really easy light to scatter? Roy G. Biv. Violet is easy. What's even easier? Well, violet is the easiest. Indigo, right? It's that whole purplish stuff. You can't really tell the difference. It's purplish. The sky starts turning purple, right? So and then they hit space, nothing, right? But if you were, it'd be cooler to take pictures. I don't know. NASA should do this, right? Take pictures as you're going up from sunset, right? You got the red sky, and then it's going to go through the whole spectrum. Okay. I'm not talking about dark as green as the grass, but it's a hue. It's a hue because it's light that's being scattered preferentially. Okay. Yeah, they didn't take pictures, probably. Okay. Nothing. Yeah, nothing. Because you're on the other side of the planet. Okay. Photoelectric. Oh no, second type of scattering. Okay. Raman occurs when scattered radiation changes frequency. In other words, energy is either lost or gained during the scattering process. So which one of these, Alice, is possible? A Raman spectrophotometer or a Rayleigh spectrophotometer? One's possible, the other one's not. Which, and Rayleigh is? All right? Because if we want to get a spectrophotometer, we want to see, light being attenuated or absorbed or something, right? With Rayleigh, there's no change in frequency. But Raman, there is. So Raman, there's Raman spectrometers. There are, right? Okay.
I'm pretty sure they changed some regular things too.
We don't have a Raman spectrometer, but photoelectric effect. Okay. Yep. Frequency. So if you're a Raman scatterer, blue light strikes you. That's a good question. Roy G. Biv. No, I'm going to say green. Green light, Ashley is a Raman scatterer. Green light strikes her. What color could bounce off? Or scatter off, a better word.
From the green?
Yeah, she's green. Sorry. Green light is incident. What color would bounce off?
Would it be blue?
Right? She's a Raman scatter. She's gonna suck up some of that energy, right? She's a Raman scatter. She's gonna start vibrating, rotating, something. She sucked up some energy from that incident light. So you have to go to a lower energy. So you would be, yeah, yellow, orange, red, right? So you can actually do some spectroscopy there and.
So with the Raman, it's always going to be less left.
Now, good question. I would say this way is easier to understand. Yellow, orange, red. However, that molecule, remember, energy's quantized. So she's got to be doing this whole vibrating thing or something, right? So this light is incident upon her, which exactly matches some other vibrational frequency. She drops an energy, that energy is transmitted to the light and it shoots off at a higher energy. So now she overall has a lower energy. She went down in her energy.
So what happens when it's red?
So it can go either way. But I think it's much more common and it's more it's easier to understand, losing, her absorbing energy and exciting some vibration. Okay.
Like when I said if it was red, then
If it was red, well then
What about black?
it would infrared, right? You just can't see it, but okay. What is black? Absence of Roy G. Biv. Doesn't mean absence of light. You can still have any of the other regions of the spectrum. Photoelectric effect. Let's take a look here. Okay, so I'm shining maximum intensity of, looks like 740 nanometers on this little hunk of metal, and I've got a positive 8 volts over here. So all we're doing is we're trying to shoot out electrons, right? So if I start going this way, is the energy getting higher or lower? It's getting higher, right? Right? Red was shorter wavelength, exactly. All right, so keep going, keep going, keep going, keep going, keep going. Finally, electrons are starting to get kicked out, and they're hitting this plate because it's positive. If I change the polarity, ooh, right? They get kicked out, but they just don't go very far. Okay. Now, does intensity matter? Where's intensity? This guy. But intensity. All intensity does is just changes the current. Intensity doesn't determine whether something's kicked out or not, right? Because intensity was maxed out in the red, and nothing even got kicked out. So you don't get this constructive interference and photons add energy and kick stuff out. No. Either a photon has enough energy or it doesn't. So in this case, this is light acting like a wave or a particle? A particle. Because particles don't add up energy. You throw Rob and I across the room, we don't get any constructive interference going on here. But if we're both acting like a wave, you would. So, definitely. Okay. Light acting like a particle. Good. Atoms and molecules are always in quantized energy states. They can undergo transitions between these energy states by absorbing or emitting light. So we have motion. You can have electron motion about the atom or molecule, right? Orbitals is a word that we use a lot, orbitals, to describe those sorts of that motion. You can have vibrational motion in molecules, like things, one atom going out, the other one going in, right? Scissors motions and all these different types of motions called vibrations. Okay. Rotational motion of molecules, like the microwave doing what to water, making it spin, it generates all this heat, right? Or you could have the nuclei spin themselves. Okay. So, which one of these is the most energetic? Changing the electronic structure and the distribution, or just taking a little nuclei and having it spin? Yeah, it goes up, right? So this is energy going up. Takes. Okay, so now let's see if we can attach some names to these things. What type of spectroscopy is the most energetic one? You're changing these electronic transitions. Now the only thing you really have to work with is understanding the electromagnetic spectrum, right? And realizing what each instrument is using. Like, for example, the FTIR is using IR, right? The UV-Vis spectrometers is using UV-Vis. The NMR is using, magnetic, but radio waves.
So would the top one be like gamma or X-ray?
Well, we don't have an instrument that has gamma or X-ray. But we have, what's the highest energy out of all these I've talked about? The UV-Vis, right? So the UV-Vis has to be this one. The UV vis is the one that's involving electronic transitions. The ultraviolet visible spectrophotometer. Vibrational motion, IR, FTIR. The rotational motion. Now, the only way you're going to know this, I think, is if in PChem we're going to analyze the rotational motion of hydrogen chloride or something like that. We're going to use the FTIR to do it. So infrared region is both vibrations and rotations of complete molecules, though. The entire molecule has to be spinning. So spinning nuclei would be NMR. Okay, we're almost done. So you have in all these types of spectroscopy, you pretty much have a sample. You have some incident light, and then you have your transmitted light. I think the book uses P's. That's why I'm using P's. So incident and transmitted. Incident and transmitted. Intensities. Incident and transmitted intensities. So you can calculate transmittance. Well, that's just whatever got through. It might be attenuated a little bit all over the incident. And if you want to make it percent, fine, multiply by 100. Absorbance is negative log of transmittance. All right. So that's one way to get absorbance. The other way to get absorbance is EBC. C is concentration. B is, well, it looks like B is what in our little diagram there?
It's the length
Yeah, like the width of the cuvette or something. They call it path length is the technical jargon. Path length. Okay. And little epsilon. Yeah. They call it an extinction coefficient. Now, this bottom one, actually all of these, should have a little wavelength subscript because all of these things. Now, does it make sense to put a little wavelength on the subscript on the B? No, because they all have to pass through that cuvette, right? So don't put one there. Does it make sense to put a wavelength on the concentration? No, it's just concentration. That's not going to change. So for each wavelength has its own absorbance, has its own extinction coefficient, path length, and C. So once you know the molar extinction coefficient for a certain wavelength, you can always calculate concentration. Just measure the absorbance, the path length, and you'll have it. Okay, so that's enough for one day.